So if you just click on that, it should download, and you should be able to click on it, and it will open up in R. And then we're going to do library. R commander. Yes. Pardon? Yeah, but I'd like to get going and do that next week. We just have a very short week this week. All right, and you might have to click on the data set location, so Halibut Fix will come up. And we're not going to jump right into analysis. I'm going to go through what we're doing today with the movies first. Everybody got it? Are we all sort of sitting there? Then the second thing we're going to do is go to third, can't count. We're going to load the R Commander plugin under Tools, and we're going to load the KMGG Plot 2, restart R Commander, and reselect Halibut Fix. Are we all good? All right, so there's a couple of things we want to get to today. First of all, we're moving back to the graphs to analysis section. And so there are a couple of stages in data analysis, and the first one is descriptive, which we've done, which is calculating your means, your medians, your modes, your standard distributions, that sort of stuff. That's just telling us what our data is about. The second stage we typically do is exploratory. All right, that's where we just start graphing things to see what might have a relationship with something else. We have asked specific questions, however, and that's inferential. And sometimes people confuse that just because you're graphing, you're in exploratory. Exploratory means you don't really have a hypothesis that you're going to test. Inferential means that, there's an M missing. Inferential means you want to make an inference. You want to use the data and the test, just ask the question. Exploratory, you're just bouncing around graphing stuff to see what you might get. You can run models that are exploratory. Okay? Exploratory just means you don't really know. Typically, and people who don't know stats think graphing is exploratory and models are inferential. You can run exploratory models, and the final one is predictive. Okay? And so we have done that. We'll walk through this. We'll show you an exploratory. We'll do inferential, and we won't do predictive today. But we do predictive analytics in this class because they run your life and you should know how they work. You should know how you're being targeted and nudged to buy things or do things. And we will show you how that's done a little bit later. All right, so we have our Halibut Fix up here. All right, and if we were going to do our descriptive statistics, we could do summaries and hit the active data set and say OK. And it would bounce through very quickly and give us the standard set of means, medians, first quartile, second, etc. All right? You don't know what these variables mean, but running a set of descriptive statistics in modern data sets is usually 2 clicks, sometimes 3. And so we have it, all of the variables here. We'll walk through the data set a little bit with it open in a data view. All right? So clear that to get descriptive statistics, we go up to statistics and summaries, and we could have done a few more down here if we wanted. but essentially you can run it on the active data set. All right? So, and those are the primary set of descriptives are over here in the summaries. I don't spend a lot of time on descriptives in this class because you've done them in intro, you've done them in biolab, you'll see them again, and other than for data cleaning, they are not useful in writing paper. Right. Until you get to the exploratory part, if you're putting in the mean laws and the standard deviation laws and variables in paper, you're wasting the reader's time because they're just going to skip over it. And no modern editor will let you put that in a journal. If I see that stuff, it's put it in an appendix, please. But it shows. But what it immediately kicks off, if you're putting that kind of data in a paper, in a modern publishing framework, is that you don't understand your statistics well enough to be doing them, and it sours the people for the rest of it. That doesn't mean, if you have a professor here who tells you to put the descriptive statistics in, that you don't do it. I'm just telling you that if you're trying to get published, it better be meaningful or don't do it. All right, so the next thing we're going to do is we're just going to do some exploratory, all right? And we're going to do exploratory graphics, and we're going to graph a bunch of things by a bunch of other things. But first of all, let's open the view data set, and I'll tell you what we're looking at here. All right? So what we have here is a skate. This is halibut fishing. We're catching fish. This is commercial fish data. And a skate is a long line of hooks that halibut come up and take the bait on, suffer for a couple of hours, and then are dragged onto the boat. This is the depth in feet where the skate was basically running, how many skates were run off of that boat, the pounds of legal halibut, the number of halibut, how many of them, number were legal, how many were sublegal, number of saving fish, rockfish, and then where they were caught, and the year they were caught. All right? This, and what we're looking at here was to see if the change in rules on the number and length of skates that were put in had an effect on illegal fishing, or on, not illegal fishing, it's legal fishing, but how much take that was on fish that were the wrong size. All right, so we wanted to see if the rules worked. All right, so that's our data set. And so let's go to ggplot, and we're going to do a scatter matrix. And let's do depth, effective skates, grab those three, grab the top three, using the control key and click on them, and we're not going to do any stratification or anything. And then come down and grab the cod, rockfish, and sablefish. And we're going to do smoothing with a confidence interval. Right, we're not testing anything. I'm just grabbing a bunch of variables and plotting them against one another. Okay, and this will take a while because there's a bunch, because there's 14,000 observations. This is also where I pitched the Fisheries Observer Program. Anybody know what the Fisheries Observer Program is? If you've had 36 credits of biology, you qualify to be a fisheries observer. Anybody interested? You qualify to get on a boat with a bunch of really stinky fisher people and do measurements that will go into databases like this. Anybody still interested? You make about $6,500 a month. Anybody interested? All right. It's a fairly popular thing for students to do who are in bio and environmental, etc., who get to their career at the end of this and they're like, I'm not really sure what I want to do. All right? Your first tour is in Alaska, which totally sucks. Your second tour is in Alaska, which totally sucks. Your third tour is on the Great Lakes, which really sucks. And then you get to do the Hawaiian Islands. All right? So, right, and then the people who actually make it to the Hawaiian Islands, they stay observers till they're about 35. All right, so, but if you get stuck and you don't have work, talk to me, we'll get you in at observers. The people who've done it from Japan have loved it. Mostly they've loved going to graduate school and spare $18,000 a month. It's not bad. All right, so we're looking at this. Do we see any relationships? Fish people, are there any relationships in this? Do we see anything that looks like it might be positive and significant? Or negative and significant? Do you catch cod deeper than rockfish? I shouldn't even have to ask this if you know fish, but should need data, right? Bottom dwellers. All right, are people seeing this? So this is exploratory data analysis. We just plotted a whole bunch of things, and then we're like, okay, which ones of those look like they're positive, and which ones look like they're negative? Would they be significant? And we're la 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 la. It's all great. All right. Do people understand that? And then these are just the distributions of those variables. Do any of them look even modestly normal? Yeah. So that's sort of what we're doing. We're bouncing through here, seeing do you understand why this is exploratory? I have no hypothesis in mind. We can run this. This is the visual version of going to statistics, summaries, and correlation matrix, and choosing the same set of variables. Okay, I stretched mine out and reran it so that I could see the matrix here. And we see the correlations here. Some of these negative means, so we go down from depth, and we see skates positive, more skates deeper, halibut deeper, no, rockfish is, both of these are shallower, right? Negative correlations mean shallower with depth. Rockfish and sablefish both go more. And then if we want to look at rockfish and the correlation of rockfish with sablefish, we see that it's 0.12, not very high, right? These are between -1 and 1. 1 is a perfect correlation, -1 is a perfect negative correlation. Anything negative means they go in the opposite direction. Anything positive means they go in a positive direction. Does that make sense? People understand correlation. You've seen it before. They claim to do it in intro. That correlation is effectively the slope of this. So if correlation is down, this line is going to be down. If correlation is up, this line is going to be up. Okay? And then we bounce over, and if we want to know if those are significant, we can look at our two-sided p-values, and you see that we have 14,000 observations, right? Once you get about 10,000 observations, lots and lots of things become significant, but it's less meaningful when you have a lot of significance because everything becomes significant if you have enough observations. All right, are we clear what we've done? So we've now done our exploratory analysis. Now we want to go back and actually test some hypotheses. So let's go ahead and we'll do a box violin plot here. And we want to know if the effective skates set led to more halibut pounds legal. Okay. So we want to know, is there a relationship between number of mile-long fishing lines and the catch? So if you set more skates, did you get more fish? That make sense? So we're going to go ahead and just leave that as a box plot and say okay. And oh my goodness, we had way too many numbers there, right? Because they're not ones and twos, they're margins. So let's see if we have one of those that's we have one called skate factor in there, which is rounded, right? So we just rounded to the skates so we don't end up with that. So let's go ahead and rerun our box plot. And we'll do the skate factor, we're going to do skate factor, and we'll do halibut pounds legal. We'll do our box plot again. And this should be a little more reasonable. All right?
What were the variables you selected again?
They're right there. So if you wanted to reduce the catch, and you want to make a policy, does this data suggest that you could reduce the catch by only allowing 5 skates, eliminating the number of skates? Yes? No? What do you think from this data? Yeah.
I think maybe there's a bigger jump from 4 to 5 than 5 all the way up to 8.
So yeah, so there might not really need to be any different. Yeah,
So
so
I don't think it would be significant if it was only 10 to 5, maybe 10 to 4 or 30.
yeah, so if these guys set 6, 7, and 8 and only set 5, you want to move that down to 3. So let's go ahead and create a variable for that. A skate's less than 5. So we'll go to data, manage variables. We'll compute a new variable, and we'll call it skate LT 5 for skate less than 5. And the expression over here, we're going to put a parentheses in. We're going to double, and we'll do less than 5, and times 1. And the times 1 just turns it into 0 and 1. And then everybody got it? Then we're going to say OK. And now that will have put that into the data set. So if we view our data set, we should have zeros and ones in there, do we? All right, so we'll go ahead and close that. Now we want to turn that into a factor, so it's not zeros and ones. So we're going to turn it into a categorical variable. Go to Data, Manage Variables, and we're going to convert a numeric variable to a factor. We're going to select our skate LT5, and we will supply the level names. And we're going to leave it same as the variable. We'll say OK. And yes, we are going to overwrite it. And 0 is more than, well, it should be 5 or more skates, sorry. Yeah, I'll do less than 5. Okay. And there's nothing magical about those names. You could have put your own in. And okay. All right, did it run? Anybody with errors? All right. Let's go ahead and do our KMGG plot. We're now going to do a box plot, but we're going to use that variable. The skate less than 5, the halibut pounds legal. And we'll do a notched box plot this time because I want to talk about notches. Okay. Probably would have been good to make them, to use names that would have been alphabetical so that grayer was up. Now do we buy the hypothesis that 5 or more leads to, so if we wanted to set a policy, we would say you have to have less than 5 skates. Does this make sense? All right, so then the point, we are now in inferential, right? Because we're making an inference about whether these are whether a hypothesis could be tested. And I put the notches in because if this notch doesn't overlap that notch, you see this little tiny notch in here? Hard to see, doesn't overlap that notch, then these are statistically significant. Or we'll be using a Mann-Whitney-Wilcoxon or a Kruskal-Wallis. They almost never give a different result, so people argue about which one to use, but they almost always give exactly the same significance. So, all right, are we clear? So then we have this plot, so go ahead and grab this plot and copy it as a bitmap or a metafile, whatever you want, and open up Word. And paste it in. All right. So we have a box plot here. What test do we run with a box plot? Ruskell-Wallace, sure. Hopefully that will work. So we're going to go to statistics, non-parametric, and a Ruskell-Wallace test. And it will be the skate less than 5 and halibut pounds legal. And okay. Are we significant? Yes. So now, please copy your Ruskell-Wallace chi-square here. Copy this line, right-click and copy. Go to our Word document, right-click on and insert caption. And figure one, leave it at figure 1, whatever you want. Number of skates versus legal catch. And okay. And then I'm going to do a Control V and put my all right. So everybody got it? All right, and then in there, what I wanted a copious caption here would be, if somebody was visually impaired and could not see this, then you would write the box plot for the 5 or more, had a median of 545 versus the box plot for less than 5 skates of 333. The KW test was highly significant, but may have issues due to the lack of symmetry in the 2 groups. Okay, you don't know that, but we will soon. All right? Okay, is that clear? That what I want in a caption? I want you to say what's in the picture. I want title, and I want the stats in the caption. Okay, so it's now both visual and statistical. And you can put more in here, and it won't hurt you. Right? You can put more in here. You can put that there were 14,500 observations. That would be good. Yes? Yes, you would have your data citation in there. The copious captions for me have the data citation. And the reason for putting that in there, for getting everything in your caption, is that if you have to reuse this, the more you put in your caption, if you want to go back, particularly if you're doing these in PowerPoints, and you're doing presentations, the more in your caption, the easier it will be to rewrite this, right? The easier it will be to rewrite this. And I think you will find that it will make your research life better if you make copious captions. The other thing is if you have to talk about it, and you give the talk, and then you're asked to give the talk again 6 months later or a year later, and you're looking at it, and somebody says, well, how many observations were there? And you're like, a lot? Right? If you've got it right there in the caption, don't be snarky like I do and say, well, read the caption, but it's there for you. All right? Does this make sense? So what's the, but then you're going to have somebody who hates non-parametric tests, which is what we just did. All right? There's going to be somebody who hates non-parametrics and they want a t-test. Okay? So your job now is to go run the appropriate graph and a t-test. Come on, help each other out. I know one of you knows the appropriate graph that goes with the t-test. And what kind of error bars do I hate? I hate two kinds of standard errors, and even more than that, I hate standard deviation error bars because you can't draw any inference from them. If you're doing descriptives, they're great, but if you're testing a hypothesis, so which one? Nope, we're going to do the KMGG plot. We're back to our violin plot, except we're doing a t-test, therefore, the one that says t-test. No, we're just doing exactly the same plot that we did before, except we're doing a t-test